In section 5, we're going to be working on functions, and the goals for this section are to be able to determine whether relations between variables are functions, and to use function notation, to find the domains of functions, and to use functions to model and solve real-life problems. Also, we want to evaluate difference quotients, which is sort of a lead into calculus. So talking about functions, the definition of a function is that a function is a relationship in which, for every input, if you think of these as inputs, there is only a single output. Right? So you'll notice in the lines marking when my input was 1, my output was 9. When my input was 2, my output was 13. When my input was 3, my output was 15. When my input was 4, my output was 15. Now you'll notice that both of these inputs share an output. That's okay. This is still a function. It would be if one of these inputs had 2 outputs that it would cease to be a function. Okay, and when we talk about the collection of all the inputs, if these are all the inputs, that would be called the domain. The inputs are also typically known as the independent variable. Okay, when you look at our collection of all the outputs that we have, the collection of all the outputs is called the range. And the output variable is also called the dependent variable. And it's called the dependent variable because it depends on what the value of the input variable was. Okay, so in the independent variable, it's independent because you're free, your choice is independent in terms of choosing inputs. And then the output is called the dependent variable because its value depends on what the input was. So when we talk about, this is really formal, the way they're describing this, characteristics of a function from set A to set B. Each element in A must be matched with an element in B, meaning for an input, I must have an output. Some elements in B may not be matched with any element in A. So you'll notice I've got all these different possible outputs, but they're not actual outputs. 2 or more elements in A may be matched with the same element in B, meaning here 3 and 4 are both matched with 15. That's okay. But an element in A cannot be matched with 2 different elements in B. And that's what we talked about. For any input, any input cannot have 2 outputs or it ceases to be a function. Okay, there are 4 different ways, primary ways to represent a function. We can verbally describe how the input variable is related to the output variable. For instance, I could say at x, for every value of x, the output would be squared and divided by 2. That would be describing it verbally. Right? We can describe it numerically by providing an input-output table, a table or a list of ordered pairs that shows you how the inputs match with the outputs. We can show it graphically by graphing the items, so putting all the points, or perhaps we could even do bar graphs or things like that, depending on the type of values you're showing. And we can also show it algebraically by showing an equation. So don't confuse the verbal description with the equation. They're different things. Okay, if you take a look at testing for functions, what's one of the first things we want to know is be able to look at some of the different representations and decide, is this a function? So we're looking as, does this represent y as a function of x? Meaning for our independent variable, our input x, outputs of y. So when you look here, this is a problem. If you've examined these, you notice 2 matches up with 3, but -1, it matches up with both 3 and 4. Okay, that means it is not a function. This is one input that has 2 outputs, not a function. Okay, so that's what it looks like in this type of representation. If we look at it here, the easiest way to look through an input-output table is look and see, doesn't a single input show up more than one time with a different output? So I have 0, 1, 2, 3, 4. All right, these are all individual numbers. None of them repeat. This shows a function. Okay? So that's kind of what you're looking for. If I had in an input-output table something like this, -1 would show up twice in my input line, once with the output of 3 and once with the output of 4. And that would be an indication it was not a function. If we want to test for functions that are being represented algebraically, we would want to take a look at, and mostly what we're talking about is we're talking about solving for y, right? So if I put it into the form that we would expect for a function, meaning y equals. That's why your calculators have a y equals set up in graphing. They're made to graph functions, which makes it's a limitation to your calculator because it doesn't graph things that aren't functions. If I take the square root of either side, I'll get y is equal to plus and minus the opposite of x squared plus 8. Well, this plus and minus, this indicates a problem, right? Whatever value of x I put in, I'm going to find both a positive and a negative version of that. That's 2 outputs, 2 different y values for every x value. That makes this not a function. Over here, if I put this into a standard form for a function, meaning y equals. By the way, we also have function notation. This and this are the same. This is standard notation. This is function notation. Right? Now you notice that for any value of x that I plug in, I'm going to get one specific value out for y. Right? Nothing's going to happen when I plug in a value of x that would create 2 different y values. So this is a function. All right, so let's look at evaluating a function. Now when they say evaluate the function, they're basically saying plug it in. What do I plug in? I plug in whatever's in these parentheses in function notation. So we're back in function notation. Function notation, by the way, was created by a Swiss mathematician called Leonhard Euler. He also created Euler's number. Surprise. What f of 2 means is take 2 and plug it into this function in place of x. And then I would follow order of operations. 2 squared is 4. 4 times 3 is 12. I'll have 10 minus 12 equals -2. So the function of 2 is -2. This would be my solution. Same thing here. If I want to find the function of -4, I take -4 and I plug it into the function. -4 squared is 16. 16 times 3 is 48. So I'll have 10 minus 48. So my function of -4 is -38. Okay, this was nice and tidy because they gave me numbers. I plugged them in to my function and I got out numbers. Okay, so that's real easy, but that's not the only thing I can do. Here they're asking me to plug a binomial in. All right, so I'm actually putting in an expression and I'm going to get out an expression. Okay, so I have 10 minus 3 times x minus 1 squared. So you'll see it doesn't matter what item gets put in these parentheses. What I do with it stays the same. I plug it in. Where do I plug it in? I plug it in place of x. It replaces x. I substitute it for x. 10 minus 3 times x minus 1 squared is x squared minus 2x plus 1. When I distribute the 3, I'll have 3x squared. I got to keep these parentheses on at this point. Minus 6x plus 3. And then when I distribute and take the parentheses off, I'll have 10 minus 3x squared plus 6x minus 3. Because remember, I'm distributing negative 1. I could have done it all at one time. I could have multiplied by negative 3. Okay, if I had done that, it would have looked like what I end up with here. I'd have 10 minus negative 3 times x squared is negative 3x squared. Negative 3 times negative 2x is plus 6x, and negative 3 times 1 is minus 3. So you see I get the same thing. And then I want to combine like terms, so I'll get negative 3x squared plus 6x. I'm also putting it in the correct order, and I have 10 minus 3, that's going to be plus 7. So the function of x minus 1 is this new polynomial. Okay, that is my answer. So it doesn't matter what gets put into the parentheses in function notation. You plug it into the supplied function, and then you simplify. Okay, now a piecewise function. It's probably been a while since you've looked at piecewise functions. Piecewise functions take the set of inputs and break them into different sets. And the sets are broken up by these conditions. I use one function for values of x that are less than 0, and then I use a different function for values of x that are greater than or equal to 0. So the first thing I have to determine is, where does this value fit? Well, negative 2 is less than 0, so I plug it into this function. So the function of negative 2 would be equal to negative 2 squared plus 1. Negative 2 squared is 4. 4 plus 1 is 5. That's the answer. Okay, when I pick 2, well, 2 is greater than or equal to 0, so I'm going to plug it into this other function. 2 is equal to 2 minus 1, which equals 1. And 3 is also greater than 0, so I plug it also into that second function. 3 minus 1 is 2. Okay, so when you're working with a piecewise function, first you have to figure out which condition does your supplied input fit. And then you know which function to plug it into. Okay, does that make sense for everybody? Hopefully, yes. Okay, finding values for which f of x is equal to 0, or we might call this finding zeros, or we might call it finding solutions, or we might call it finding x-intercepts, or we might call it finding roots, because zeros, solutions, x-intercepts, and roots, they're all the same item for a function. Okay, so when we want to find all the real values that f of x equals 0, when f of x is this function, so I want to say, right, I want to find, I'm not finding f of 0. I'm not plugging 0 into the function. I'm setting the function to be equal to 0. And you're used to that with quadratics because that's what we do to solve them. So in this case, I'm going to factor. I can see this is the difference of two squares. So this factors to be x plus 4 times x minus 4. And then the values of x that will make these equal 0, if I want to be really explicit, there's a rule, it's called the zero product property, that says if I multiply a bunch of things together and the end result is 0, then one of these things, one or more of these things, must have been equal to 0. Because that's the only way to multiply two things together and get it to equal 0 is one of them had to equal 0. So when I solve, I set each of my different items to be equal to 0. And I solve. So I subtract 4, x is equal to negative 4 for this one. And over here, x is equal to 4. So 4 and negative 4 are my solutions. Now, do you have to write it out like this? No. When you get really used to it, you look at the binomials and you go, oh, negative 4 and 4. Easy, however you get the solutions. But if you're confused about what the solution is, take the different terms, set them to be equal to 0. Or sorry, take the different factors and set them to be equal to 0. Solve each one and you'll get all your solutions. Oh, so this is a little different. Finding values for which two functions equal each other. Okay, this is a lot like what we do when we do substitution and combination, only a little different. What I'm going to do, though, is I'm going to set, right, to find the values of x where f of x is equal to g of x, I make f of x, I know this is going to be a shock to you, I make it equal to g of x. And then I'm going to solve, right? So I'm going to add x squared to either side. I'm going to subtract 4x from either side. And now I have a quadratic or a polynomial that equals 0, and I'm going to find values of x that make it equal 0. The first thing I do is factor a 2 out of everything, so x squared plus x minus 12. I want factors of 12 that have a difference of 1. That's 3 and 4 has to be positive, so it's x plus 4 times x minus 3. My solutions will be -4 and 3. So for these two values, f of x will equal g of x. Okay, so when we start talking about the domain of a function, okay, so we have an assumption. There is an implied domain when you start a problem, that the domain is the set of all real numbers, that there are no limitations on what I might choose for x. And as you work with the problem, there may be numbers that can't be used. Okay, or in the case of this first example where they gave me a discrete set of values. These are all the values, so my domain is limited to these values here. So I'm just looking for, in the domain, I'm just looking for the inputs, just the x values. Okay, so my domain would be -2, -1, 0, 1, and 2. That's my domain. Okay, so when they give you a limited set of values, and that is all the values, then you just identify all the inputs, which are the x coordinates, or x values in ordered pairs, and you collect them as the domain. If they asked you for the range, you would do the y coordinates. Okay, but that's not what they asked for. Now let's look at a new problem. Again, I'm going to assume that there's an implied domain of all real numbers. But I look at this and I go, well, I know that I'm not allowed to have 0 in the denominator of a fraction. So when the variable's in the denominator of a fraction, that creates a limitation. I cannot use the number 3 because 3 minus 3 equals 0, and then for this function, 3 would be undefined. It's not a number I can use. So you could express the domain as x does not equal 3, or you could say it is all real numbers except 3. Either one of these potentially could be the way you express your answer. Okay, I generally do this one because it's faster and it's simpler and my handwriting sucks, so it's easy to read as well. Okay, moving on to number C, when you look at, okay, now this is a little different. With circumference of a circle, our input value is the length of the radius. Okay, so in this case, x's would be this value r, and y's would be the circumference coming out. So x's would be the length of the radius, y's would be circumference of a circle. 2 and pi are both constants. So you want to look at this and go, okay, there's an implied domain of all real numbers. Is there any number, any value of r that I could not use for the circumference of a circle? Well, yeah. My radius is a distance. It can't be 0, or it's not a circle. And it can't be negative because that's not a measure of distance. So my x values have to be greater than 0. Okay, otherwise it's not a circle. Okay, and when we measure the length of the radius, the distance from the center to any point, negative doesn't come into that. We don't measure negative distances. Okay, because direction in this case is not part of the question. Okay, if you look at this particular problem, again, I'm going to assume it's all real numbers, but I'm taking the square root of a value. I know that I cannot evaluate in the set of real numbers the square roots of negative numbers. Okay, so any value of x that will result in a negative number, I can't use, because then we'd move into imaginary numbers, and right now we're keeping our attention limited to real numbers. Okay, so any number, the smallest number I can have here is 16. 16 minus 16 is 0. I can take the square root of 0. It's equal to 0. But as soon as we go below 16, this is going to result in negative numbers, and I can't find their square root. So my x value has to be greater than or equal to 16. Now you notice here it was okay for it to be equal to 16, but here it was not okay for it to be equal to 0, because a circle with a radius of 0 is not a circle. Okay? So you just want to think about the problem. There is no, outside of examining it, the equation, and thinking about what it means and what it represents, there isn't like a set of steps that I can tell you for the domain. Okay? You just have to know what you understand about the rules of mathematics and apply them to each individual circumstance. Speaking of applying them to an individual circumstance, we try to apply these concepts to real-world application. Here I'm working for a marketing company of a soft drink, or marketing department of a soft drink company, and we're looking at making a new can for our iced tea. Here's our new can. And for our experimental can, we're going to have a ratio of the height to the radius that equals 4. Okay. So the height divided by the radius is equal to 4. If I want to write the volume of the can as a function of the radius r, okay, that means where I have height, I'm going to need to replace it. So here's my ratio. H over r is equal to 4. So if I want to find the value of h, I multiply both sides of the equation by r. So h will be equal to 4 times r. Because when I start writing this volume function, I'm going to have height as part of it, because it's the circumference, the area of the circle at the bottom times the height. That's what we would do for the volume of a cylinder. So as we look at the A part of this, I know that my volume of a cylinder is going to be the area of the circular base. Area of a base is pi r squared times the height. And remember, the key in this is that they asked me to, as a function, write this as a function of the radius r. I'm not allowed to have height in there. But they gave me this as extra info, so it's going to be pi r squared times 4r. Because 4r is the height. So when I finish this out and simplify, I'm going to get 4 times pi times r cubed. And this is my volume for this can. If I want to write the volume of the can as a function of height, now what I have to get rid of is I have to get rid of the radius. Well, if I take this same formula and I solve it for the radius, if I have h divided by r is equal to 4, I'll multiply both sides again by r, 4r, and divide by 4. Height divided by 4 is equal to the radius. So now I can take this item and plug it in. Right? So volume will be equal to, again, let's just go ahead and write it out, pi r squared times height. And in this case, r was h divided by 4 squared times the height. And now I'm going to simplify. So my volume will be equal to pi times h squared over 16, that's h over 4 squared, times h. And if I put this all together, I want to be really explicit with this. pi is pi over 1 times h squared over 16 times h over 1. Right? When we multiply fractions together, I multiply the numerators. So my volume will be pi times h squared times h. That's going to be pi h cubed over 1 times 16 times 1. Should be 16. This would be the best way to write it. I could also write it by breaking the denominator out and make it 1/16 pi h cubed. Both of these are correct. Right? I would probably write it as the first one, but the other one is correct as well. Okay, so you'll notice then I took this ratio of h divided by r is equal to 4, and in these cases we used them in two different ways. Right? I solved it for h, and then I took the value that h was equal to and I substituted in my equation in place of h, so that I had a volume only as a function of the radius, r. So we eliminated h from the equation. And in the other problem, we eliminated r from the equation. We found h divided by 4 was equal to r, and so we plugged that into the function in place of r. Now I have a function that's totally related to the height. Okay, you just want to do whatever makes the most sense in terms of the work you're doing. Okay, here's another piece of work here looking at applying these concepts to some sort of real world construct. A second baseman throws a baseball toward a first baseman 60 feet away. The path of the baseball is given by this equation, where the function of x is the height of the baseball, meaning the output is the height of the baseball, and x, the input, is the horizontal distance from the second baseman in feet. The first baseman can reach 8 feet high. Can the first baseman catch the baseball without jumping? So let's go ahead and rewrite this a little bit. I'm going to say that height is equal to negative 0.004x squared plus 0.3x plus 6. Then we know that the distance it needs to be from the second baseman when the first baseman gets them is basically 60 feet. I guess we're ignoring the concept that if the first baseman can reach 8 feet high, he could also reach forward a certain distance, maybe not 8 feet, but something close. We're ignoring that for the time being. So the idea here is that if my resulting value is somewhere between 0 and 8 feet high, then he can catch it without jumping, and if not, he'd have to jump or it would just go over his head. So the key is my input, which is my x value, is 60 feet. That's how far away from the second baseman it needs to be when it gets to the first baseman. So I plug that in. Negative 0.004 times 60 squared plus 0.3 times 60 plus 6. Right, so when we have 60 squared, we're going to have 3,600 times 0.004 plus 0.3 times 60, right, which is basically a third, a little less than a third. That's 18 plus 6. I'm going to pull out a calculator. This is going to be plus 24 when I combine the 18 and the 6. I'm going to pull out a calculator for this one because I don't really want to do it in my head. I imagine I could, but why would I want to? So 3600 times 0.004 equals 14.4. So we're going to have negative 14.4 plus 24. That equals 9.6. So can he catch the baseball without jumping? No, the bell's up here. No. Hopefully he can jump 1.6 feet. I bet he can, and he can still catch the ball. Okay, if we take a look at this example for alternative fueled vehicles, now you'll notice right off the bat what I notice is that I have conditions on which function, two functions, and conditions under which I use the different functions. This is a piecewise function. So when I figure out my value of t, I'm going to have to figure out which condition it meets to know which equation to use. So that's just the first thing I see in looking at the problem. I note the number V in thousands, okay, of ethanol-fueled vehicles in the United States from 2003 to 2009 can be approximated by this, where t represents the year with t equals 3. So this is years since 2000. So 2003 is the year 3, 2005 is 5, 2006 is this value, and 2009 is this one. Use the function to approximate the number of 85% ethanol-fueled vehicles for each year from 2003 to 2009. Okay, I'm probably not going to do all of these, but I do want to talk about how this would happen. Okay, well actually, we'll set this up and maybe we'll go ahead and do it. So that means we want to find f of 3, f of 4, f of 5. All of those will use this first function. So that would be 33.65 times 3 plus 77.8. And this one will be 33.65 times 4 plus 77.8. And this one will be 33.65 times 5 plus 77.8. Okay, so if I look at this and I go, well, I got to do the exact same calculation 3 times, it's starting to make me feel a little uncomfortable. So I think I don't really like to do this much work, and I'm feeling kind of lazy, so I think maybe I'll look for another way to do it. And a calculator kind of sucks for this, but Excel is perfect for this. Let's use Excel. Okay, so I'm going to open a workbook in Excel because Excel is made for doing this kind of work. It's made for tabulating data. It's made for doing repetitive calculations, and this is going to be easy. So I know I'm going to have 33.65 as one thing, and then this is the value that's going to change. So I'm going to call this X. And then I'm going to have 77.8. That value never changes. And over here I'm going to put in a formula. Okay, so I'm going to want this formula to equal this cell times this cell plus this cell. And if I put in 3, it gives me the answer, 178.75. 178.75. If I go back to Excel, then I change this value. I make it 4, and I hit Enter, and now I have 212.4. 212.4. And I go back and I do 5, and I hit Enter, and I get 246.05. 246.05. Okay, those are the first 3. Now, when I get to f of 6, I have to change functions. F of 6 is equal to 70.75 times 6 minus 126.6. And then f of 7 will be 70.75 times 7 minus 126.6. F of 8 would be equal to 70.75 times 8 minus 126.6. And f of 9 would be equal to 70.75 times 9 minus 126.6. Okay, so if I go back to Excel, I could either change these values or just recreate this. I'm just going to recreate it below, just in case. Maybe I'd want to go back sometime. Do that again. Maybe I wouldn't. Right? And here I have negative 126.6. I did it as negative because I don't want to rewrite this formula. I'm just going to copy it. Okay, and you'll notice that this is the original function I wrote. It's going to take that cell, the blue cell, multiply it times the green cell and add the purple cell, right? And this one does the same. It takes the blue cell, multiplies it times the green cell, and adds the purple cell, but one row down. So that's why I put the number in at the end, the 126.6 as a negative number, so I didn't have to bother changing this formula. Okay, so now if I pop in 6, I'll get 297.9. If I pop in 7, I get 368.65. If I pop in 8, I get 439.4. And then I pop in 9, and I get 510.15. So at what point is it easier to switch to Excel when you're doing multiple repetitive calculations, and at what point is it easier to stick with the calculator? That's really up to you. What's important is that if you have Excel, or if you have access to another type of spreadsheet like that, you have Google Sheets, there's numbers in the Apple suite for, which is called, I forget what it is, Apple Work, iWork. So there are a lot of different spreadsheets. They all basically do the same thing. You decide, but typically for me, if I have repetitive calculations I want to do, if there's more than 2 or 3 of them, I often would just set it up in a sheet and redo the work. Okay, it saves you from making mistakes, right? I only had to put in one number for each new calculation, and it made it a lot easier. Okay, so now difference quotients. This is going to be one of the basic definitions of calculus. They're telling you employs the ratio about difference quotients. And this ratio is calculated using this f of x plus h minus f of x divided by h. It's called the difference quotient. So if we wanted to go ahead and find this, right, remember what this is telling me to do is it's telling me to take this and plug it in place of x. Okay, now this one is f of x. We already know what that is. It's this. So I don't have to plug x back in place of x to do that. It's pretty obvious what it is. So what I'm going to do is I'm going to start by just finding this value. Okay, so I'm going to find f of x plus h. It would be equal to x plus h squared plus 2 times x plus h minus 3. Okay, and when I square this, I'll have x squared plus 2hx plus h squared plus 2x plus 2h minus 3. And now what I'm going to want to do is I'm going to want to combine like terms, but there really aren't any, right? So we're going to have x squared plus 2hx plus h squared plus 2x. It's nice that everything's pluses except the minus 3 plus 2h. Sorry, I just said it was minus 3. Minus 3 minus f of x, which is this, x squared plus 2x minus 3. And this whole thing would be over h. Okay, now I'm going to combine like terms. Actually, I'm going to take the parentheses off. I want to go through that with you explicitly. Plus 2hx plus h squared. This is a plus out here, so I don't have to change anything when I take the parentheses off. But this is a minus, which means I need to change all the signs. So x squared becomes minus x squared. 2x becomes minus 2x. And minus 3 becomes plus 3. And this again is all over h. And when we continue on, combining like terms, I see the 3 and the minus 3 are going to cancel each other. The x squared and the minus x squared are going to cancel each other. And I have 2x minus 2x. Those are going to cancel each other. And so I'm going to get I'm going to get h squared plus 2hx plus 2h all divided by h. Now, I can factor an h out of all of that. This is h times h plus 2x plus 2 divided by h. Those cancel. And I just get h plus 2x plus 2. And there you go. Okay, so it was long. It was a little bit tedious. It was a little arbitrary. And at this moment, I don't know. I haven't shared with you a practical use for it other than the fact that it's used in other calculations in calculus. Okay, so if this felt a little abstract, it certainly is. Let's move on and review some of the things we've talked about. So a function is a relationship between variables so that for each value of the independent variable, there corresponds exactly one. There can't be none. There can't be two of the dependent variable. F is the name of the function. Y is the dependent variable. X is the independent variable. And f of x is the value of the function at x, meaning at x being this value here. Okay, so whatever I plug in there, it goes into the function. And this whole thing is called function notation, and it was developed by Leonard Euler. Domain is the collection of all the inputs, meaning all the independent variables that were used or can be used. The range are the outputs based on these inputs. So when there's a limit on the inputs, that will also generally create a limit on the range. Okay, and implied domain, when we start working on the problem, there's an implied domain of all real numbers that would only be changed if there was a reason based on the function itself. Okay, and summarizing this section, we did what we were talking about. We talked about the definition of function, we described function notation, and we created some examples of determining functions and using function notation. We talked about the definition of the implied domain of a function, and we did examples finding domains of functions. We described several different cases where functions get used to model real-life problems. And we stated the definition of a difference quotient, but yet we did not use it or apply it to anything.